Hello. Picture an autonomous sensor nodes deployed in the most remote desert on Earth. Its mission is to gather vital environmental data, but it faces a silent and relentless enemy. Extreme diurnal temperature fluctuations. We are talking about swings that exceed 50 degrees Celsius during the day and plummet below freezing at night. This isn't just an inconvenience, it's a primary cause of system failure. The statistics from the US Air Force Avionics Integrity Program are unequivocal. Over 50% of all electronic failures are directly attributed to thermal stress. The reality is even starker. A mere 10 degrees Celsius increase in internal temperature can halve the reliability of electronic components and reduce capacitor lifespan by up to 50%. Furthermore, batteries exposed to ambient temperatures above 35 degrees Celsius suffer irreversible reductions in capacity and charge retention, crippling the power autonomy essential for remote operations. Conventional cooling strategies are fundamentally inadequate. Forced air systems are highly vulnerable to fine desert dust, which clogs filters, abrades components, and severely reduces efficiency. In the Sweden desert air, the temperature differential needed for effective convection is nearly non-existent. Purely passive mechanisms cannot cool below ambient temperatures nor provide heating. And while miniature vapor compression systems offer control their mechanical complexity, vibration-induced failure risk, and refrigerant leakage make them entirely unsuitable for remote maintenance week deployment. The critical multifaceted challenge of dust, extreme temperatures, and limited power is precisely what our project, the Optimized Passive Thermoelectric Temperature Regulation System, or OPTERS, was engineered to solve. OPTERS is a holistic, novel solution. We leverage a solid-state Peltier model for effective bidirectional temperature control, both cooling and heating, eliminating all mechanical movement parts like fans and compressors that are vulnerable to dust, wear, and vibration. This is crucially supported by highly efficient, fanless passive heat transfer components within a sealed and dust-proof enclosure. But it's not just robust, it's intelligent and sustainable. The system is integrated with solar harvesting and battery storage for continuous 24/7 operation. By utilizing inexpensive, widely available components such as ESP32 microcontrollers and repurposed materials, our module achieves remarkable reliability while significantly reducing both initial deployment costs and long-term operational expenditure. It is a sustainable, high-performance alternative specifically tailored for thermally hostile environments.
Okay, so now we are going to be discussing about the scientific concepts that are going to be used in our prototype. So the first concept is that of the Peltier effect. Now what is a Peltier effect? The Peltier effect is basically a thermoelectric phenomenon where we make a junction or loop out of two different conductors with varying energy states. And when the electrons move from the higher voltage conductors or the higher energy state conductors to the lower ones and vice versa, that is from the lower ones to the higher ones, they basically cool down one side and heat up the other side. For example, when they're going from the low energy state conductor to the higher one, they gain energy. And when they go from the higher energy state conductor to the lower one, they release energy. And thus we get hot and cold side from our two different thermocouples. And then the Seebeck effect is basically the vice versa or the reverse process of the Peltier module. That is, we again have a junction or a loop made up of two different conductors with varying energy states, and now when we ourselves apply heat to that energy system or that loop, basically the electrons gain energy and go from the higher states to the lower ones and then the lower states to the higher ones, and thus the movement of electrons actually creates an electric current in that entire circuit. Main innovation or a main part of our circuit is the usage of H-bridge driver in this entire process, which is absolutely new and unique to this process. So why are we using an H-bridge driver? We are using an H-bridge driver so that we can control the cooling and heating mechanisms extremely efficiently and with extreme control without any human intervention, and you can see the entire working process of an H-bridge driver on your screen right now. Now we're going to be discussing the instruments that we have used to design our entire prototype and the entire system. Okay, so first we're going to be using an ESP32 microcontroller unit, which is basically going to be a central processing unit, and then two units of DS18B20 digital temperature sensors, which are going to basically conserve all the temperature data and also measure the temperature accordingly. Then a MOSFET-based H-bridge driver, some thermal paste on the Peltier module, solar panels, spare lithium-ion battery packs so that the Peltier module can store energy to use it later on when there's going to be no sun or no solar energy in the desert area. Then we're going to be using a PWM charge controller, which is basically going to coordinate all the kind of charges that are going to be coming into the Peltier module. And with the heat shrink tubing, we're going to be using a custom fabricated aluminum passive heatsink. There's some sealers, fasteners, and obviously our custom built low-cost Peltier module, which is basically going to be our core thermoelectric cooling or heating component. On your screen, you're going to be seeing a circuit diagram of our entire prototype where you can clearly understand all the connections and all the wirings that we have put forward to make this prototype completely work. Okay, so now for our research section, we have basically put our prototype through many rigorous tests. We have basically introduced 100 degrees Celsius or more in our prototype to basically conduct all the tests accordingly. Then we have induced 2.3 gram per centimeter cube of dust in every square meter area so that we can properly measure the efficiency of the heat sinks and the microcontroller under those adverse conditions. We have got many reruns and many revisions of this entire process, and we have taken the data many times. Then we have varied the voltages and currents through our Peltier module many times, and through that we have selected the perfect Peltier module for our process, and we have made many modifications to it as well. Then finally we have checked the efficiency of our microcontroller through using various metrics, and finally the efficiency of the Peltier module through using metrics which you are going to see on the screen right now, which is basically power in and the heat that is going to be generated or the heat that it is going to be cooled by in the Peltier module itself.
For a sensor node in the desert, the difference between collecting data and a catastrophic failure isn't just measured in days, but in degrees. Extreme heat is the enemy of electronics, causing over half of all failures and rapidly decreasing battery life. Our mission was to build a shield against this enemy. Our solution is OPTERS, an optimized passive thermoelectric regulation system, but the design is only a theory until it's tested. Our results, gathered under brutally realistic simulated desert conditions, prove its superior performance. Let's look at the data. Our key metric for efficiency is the coefficient of performance, or COP. This is the ratio of cooling power we get out to the electrical power we put in. A higher COP means a smarter, more efficient system. As this graph shows, our system achieved a remarkable COP of up to 0.87. Now let's put that in context. The chart compares it to conventional methods. A standard 4C air cooling system choked by desert dust averages a COP of just 0.25. That means our solid-state fanless design is over 3 times more efficient. It doesn't just consume power, it uses it with incredible intelligence. But a system can be efficient and slow. Our system is both efficient and remarkably fast. When we simulated a critical overheating event, jumping to 40 degrees Celsius, OPTERS cooled the core electronics down to a safe 20 degrees in just 4 to 5 minutes. Compare that to the alternative on this chart. A purely passive system takes over an hour. Conventional heat sinks take 15 minutes. We perform on par with miniature air conditioner, but without any of their moving parts, complexity, or maintenance needs. We get a vapor compression of speed with solid-state simplicity. This data table shows the real-world power intake and precise temperature control across numerous tests, consistently demonstrating stable and efficient performance. You can see the system actively managing different thermal loads while optimizing power use, leading to an overall operational efficiency of 83%. But the desert isn't just hot, it's unpredictable. That's why a unique feature of our design is bidirectional control. The system is saying that cools during the scorching day can instantly switch to provide warmth during freezing nights. This isn't just a cooler, it's a precision climate controller, ensuring our sensors operate in their ideal range 24/7, preventing battery and component failure. So what does this data ultimately tell us? It confirms that OPTERS delivers a powerful combination of high efficiency, remarkable speed, and unmatched resilience. It is not just theoretical improvement, it is a practical proven solution ready to protect vital electronics in the world's hardest environment. This thermal stability is a critical foundation that makes the entire project possible. And now my teammate will explain how we power this entire system sustainably to complete the picture.
So, what have we conclusively achieved? As the data just presented proves, our module is a validated, robust alternative that overcomes the key limitation of dust susceptibility, high power consumption, and mechanical complexity. We have created a solution that is not only efficient and durable but truly maintenance-free. By combining solid-state Peltier module with fanless passive heat sinks and intelligent power management, our module ensures reliable bidirectional temperature control with minimal energy input. The system's ability to maintain internal temperatures within a strict optimal operating range while functioning solely on solar power definitely demonstrates its viability for long-term off-grid deployment. However, the impact of our module extends far beyond its technical specifications. It represents a significant step forward in building resilient, self-sustaining sensor network. It actively contributes to several UN Sustainable Development Goals, including affordable and clean energy, industry innovation and infrastructure, and sustainable cities and communities, by enabling responsible environmental monitoring in the world's most vulnerable ecosystem. In essence, our module is more than a product. It is a scalable, energy-efficient platform for the future of reliable data acquisition in extreme climates everywhere. Thank you.